Okay, so this week's interactive case study is on the drug Vigabatrin, Vigabatrin, I think. It goes by the trade name Sabril, and it's a vinyl form of GABA and a GABA aminotransferase. It functions as a GABA aminotransferase inhibitor. So, first, we want to look at how GABA works as an inhibitory neurotransmitter. And the two images on the right hand side will show you uh, that there's GABA A and GABA B receptors, and GABA A receptors are tropic, and GABA B receptors are metatropic. And so, you just some things to keep in mind. It's as mentioned, it's an important inhibitory neurotransmitter in the central nervous system. It controls inhibitory function via chloride channels. And so you can see on the top side the chloride ion and the membranes becoming hyperpolarized. So it interacts with the neurons, makes them less likely to fire an action potential or to release neurotransmitters. And it hyperpolarizes the membrane, which discourages the synapse. Let's go on to the next slide. So I thought it was important to look at the structures of GABA and of the vinyl GABA. So you can see um, like the extra carbons on the side chain in blue, and the CH and the CH2, so that you're able to recognize those structures. Okay, so this image is a really good image. It talks about GABA Vigabatrin as an enzyme activated, irreversible, selective suicide inhibitor, GABA T. And the effect of Vigabatrin is the inhibition of GABA, the catabolism of the GABA T, and it leads to an increase in available GABA in the synaptic cleft, thereby resulting in enhanced GABAergic transmission. And in addition, some research suggests that it may inhibit glial uptake. Um, so I circled in yellow the drug, so you can kind of see that. So you don't need to worry about the benzodiazepines at the bottom or barbiturates. Those function in a different way and have a different set of side effects. But what's great about this Vigabatrin is the side effects are somewhat limited. We'll talk in the next couple of slides about what an important anti-seizure medication this has become. So I just thought that this was a good image with the inhibitory presynaptic terminal. You can see the glutamate, you can see the GABA T, succinyl, semialdehyde, and kind of like the inhibition process. The postsynaptic neurons, it never fires. Okay, so this slide is pretty simple. What does Vigabatrin do, kind of in a big picture look? Well, it increases the amount of GABA T activity, the transfer aminase, and then this in turn is going to increase the concentration of GABA in the brain. And so it's really a receptor issue, which I think the last slide speaks to. And so the receptors are not activated. In fact, they're inhibited. And it's this increase in the GABA that functions kind of to put on the brakes to those excitatory impulses in the brain, and that is what encourages seizures. So some studies have shown that it reduces seizures by 50%. It's used prolifically around the world, I think in more than 30 countries, and it was approved by the FDA in the 90s here in the US. So this drug has become a valuable tool in the search for seizure-inducing pathways in the brains. Clearly, it's had a lot of impact on those that suffer from epilepsy and other seizure disorders. Okay, so then this slide, it shows the bound structure from the software of the enzymatic inhibition of the Vigabatrin. Um, let's, you can sort of see if you look deep in the middle, the red and blue, and you can play around with it on the software. And that's just the works I did. So